Hello. Hello. Welcome everyone. We will start our session in few minutes.
Good afternoon, everyone. Welcome to today's session. I am Tanishka Chakraborty and I will be moderating today's talk. Today, we have two back-to-back events. At first, we have a tech talk organized to introduce you to one of the emerging areas in power electronics, followed by the core working committee installation for the term 2021 to 2022 of IEI IEM Students Chapter Electrical Engineering Department. Now, let's start with our tech talk on wideband semiconductors for emerging bandgap power electronics by our esteemed speaker, Dr. Ankush Bagh, Assistant Professor at School of Computing and Electrical Engineering, Indian Institute of Technology, Mandi. He has pursued his PhD from IIT Kharagpur in semiconductor devices. He has pursued his ME in power engineering from Jadavpur University, and he has pursued his BTech from WBUT, India, in electronics and communication engineering. He has a work experience as program analyst trainee at Cognizant Technology Solutions Limited, Kolkata. It's an honor to have you, Sir Dr. Ankush Bagh, as our speaker for this event. Now we would like to request Dr. Ankush Bagh to start our much awaited event with his gracious speech. Also, I would like to request all the attendees to put their questions in the comment section below. After the talk, we will take your questions in the question and answer round. With that, over to you, Dr. Bagh.
Thank you. Thank you for your nice introduction. I hope I am audible to all of you. Am I
Yes,
audible?
sir.
Yes, it's clearly audible.
Yeah. So, okay, first let me share my presentation. Is my presentation visible to all of you?
Yes, sir. It's visible.
Is this moving? The slides are moving?
Yes, sir.
Yes, sir.
So thank you once again, and thank you for giving me this opportunity to present some of our research uh, uh, in front of you. So today my topic is wide bandgap semiconductors for emerging power electronics. So basically, we are working on wide bandgap semiconductors. Now, to just to introduce this topic, I think you all know the semiconductors. What is the importance of semiconductors nowadays in electronics? And now, what is wide bandgap? See, typically the appliance or every electronic appliance we see around. So the semiconductor or the IC that is made of silicon. So, but now this silicon has a band gap. Band gap, you know that the energy difference between your valence band to conduction band, and to make any electron conducting, you need to provide that energy. So you need to take one electron from the valence band to conduction to have current through your device. Otherwise, you will not get the current through your device. So that is the band gap, that amount of energy required. Now, silicon has a typical 1.1 electron volt of band gap. Now, and this wide band gap is the material which has a band gap larger than this silicon. That means the materials or the solid state materials which has band gap or the energy difference between your valence band and the conduction larger than that of silicon, that means 1.1 electron volt. So those materials are called wide bandgap semiconductors. Now, of course, why this wide bandgap semiconductors we are interested? So, okay, I think we have the slides. So then you'll see what is the motivation behind moving towards these wide bandgap semiconductors. Why we need to leave this silicon world in case of electronics. So before we move forward, these are the students, like whatever I'm going to present here. Apart from the basics, the research work all done by the PG and PhD student. And this is just to introduce this our campus. So as introduced to you, I am from IIT Mandi. So this Mandi is located almost in the valley of your Himalayan. So here you can see we have two campuses. One is North Campus and South Campus, just back to back of a hill. So here we have our own wide bandgap semiconductors lab, where we have all the experimental facilities along with the computational softwares and all other things. So in case I think all of you or most of you are UG student, but still if you are interested in any research, anything you have in your mind, so these are the facilities which we have at our campus. So first one, you can see very small, our wide bandgap semiconductors lab, and then we have two center. One is called C4DFED, which is to fabricate all these devices, we need clean room. Clean room is there are typically few names like class 100, class 1000 clean room. So through using this term, we typically mean how clean the environment is. But approximately, you can consider these are almost like 1,000 times cleaner than even typical operation theater or OT. So these are very clean room, and to maintain that cleanliness, it's again huge challenge. So apart from that C4FED center, we have this material science center, where we have typically sophisticated material related characterization setup, like FESM, TAME, and all other things which we require to analyze all the devices and the material. So broadly, this will be the outline for our for today's talk. So first, I will introduce the topic, then followed by why do we need all these wide bandgap materials and devices for the emerging power electronics. And although there are many materials or devices called wide bandgap semiconductors or wide bandgap devices, but out of that, I'll focus on gallium nitride based devices and followed by the gallium oxide based devices, because these two are the most emerging wide bandgap semiconductors. there is another semiconductor I must mention, that is called silicon carbide. So that is also a very emerging wide bandgap semiconductor. So now, uh, if you look at the engineering opportunity we have, so because see, whenever we look forward to future, we should look forward to the opportunities we have. So we there's no doubt that we need to work for a sustainable earth, like sustainable. So for that we need to have some sustainable development, and to have that. So that sustainable development, there are typically few areas that we can look upon. So first is energy. Of course we need lot of energy for the coming future. Then drinkable water, because although the 3/4 of our earth is covered by the water, but the very few of this water is drinkable, so not the all water we can drink. And then the health, no doubt, now in this pandemic period we know how important is this sector. After that, climate, and then the food. So out of these all five opportunities, today, of course, I'll more focus on the energy. What is the importance of energy, and how the wide bandgap semiconductor can really lead to a sustainable development for our future. Now, this is a very interesting. You can see this global map. So here you can see the access to electricity. So I guess from the bottom you can see, and this the white one is where we have 100% electricity, and as we move towards the darker portion of this map, global map, that is out of electricity. So now here you can see we in India, perhaps we are among few lucky ones who has a very good access to electricity. Now when you see the most of the African country, you can see it has electricity. Look, most of the African countries have the electricity access less than 50% of its population. So which is really alarming. So that means, again, for the coming world, without electricity we cannot do anything, there is no doubt. Another interesting thing here you can see in this map, the border between your North Korea and South Korea. So where North Korea has 44% population has this electricity access, whereas of course mostly close to 100% population in South Korea has the electricity. So apart from the just demographic boundary, so this map is another motivation why we should work or why we should have clean electricity for the coming future. Now, okay, so here are few factors which is again showing us how important is this sector. So although we have a huge install capacity currently in India, that is 382.15 gigawatt as of 31st March 2020, but still you can see that 1/6 of the whole global population is out of electricity. So that is really alarming. So that means we need more and more electricity. So how to produce more and more electricity? So obviously the first thing is straightforward, generate the electricity. Like there are few sources, that thermal power plant. Here we have in Himachal lot of hydel power plant. Then the renewables, of course, this solar, photovoltaics, then wind, and all others are there. But another way we can save lot of electricity, that is by that is by using this generated electricity more efficiently. So that will try to focus how we can get how we can use that energy efficiently. So here we have another nice context. So here you can see this is for a typical, like how we are utilizing the produced energy in case of thermal power plant. So in case of thermal power plant, at best we can have thermal power plant of 35% efficient. Now if we burn 100 units of coal, so 100 units is the energy. So if we burn 100 units energy coal, and if we have this 35% efficiency in our thermal power plant, so obviously we'll get 35 units electricity after, or out of that thermal power plant. Now next is the transmission and distribution. So these are the, I think how our this overall grid is divided. Typically these are the three portion. So next we have the transmission and distribution. Now in when we are transmitting and distributing this produced energy from the thermal power plant or typical energy power plant, so those are 93% efficient. So there are a lot of conversion there, there are a lot of losses. Now this is the global figure, this 93% efficiency. Now in case of India, the loss during this transmission and distribution is very high. So perhaps it is highest in the world. So then you can see we have very less amount of units available after transmission and distribution. But still, if we consider 93% efficient transmission and distribution system, so then we have 32 units available at our home. So after burning 100 units of coal, we are having now 32 units available at our home. Now see, these are the different lamps. So if we use incandescent lamp, that the old that lamp, so which is 12% efficient. So after using that 12% efficient bulb, we can at max get 4 units. So now see, from that 100 units coal to 4 unit utilization, and in between we have lost 96 units. So due to that poor this thermal power plant, then the poor T&D this efficiency, and then finally your this incandescent bulb. So again, at max we can get 25 units after burning that 100 units of coal. So again we are having loss of 75 units of energy when starting from the coal to final utilization. So now you can understand this, if you the importance of this generated the efficient use of this generated energy is very important. So that is why, not only that to meet that huge electricity shortage, it is not that you will only produce more and more energy. Even though if we can utilize this energy more efficiently, we can get lot of electricity, and we can provide those electricity to those countries which are lacking that. So now, of course, this energy saved is the energy generated. Now, in case of this power electronics, we are having a lot of active devices as well as passive devices. So active device means there are a lot of transistors, switches, and passive devices means that your resistor, inductor, capacitor. Now, if we consider the power device, that active device, so these devices are suffering from different losses. So those losses can be typically divided into two parts. One is the conduction loss, and another one is the switching loss. So here I am considering this power device as a switching device. So because see, in this coming slide we'll just see the power device can be utilized as a switch, as a linear linear switch also. Like there are two types of application. So, but here, when you will consider this power device as a switch, these are the losses. Now, why I am showing these losses, or why this? Okay, let me take this. So see, this losses accounts to a significant portion of the electricity generated. So this is the US electricity generation scenario of 2007. This is a bit old data. So now you can see this conversion losses. So it accounts around 10.5%. Now if we compare this loss, this conversion losses with other generation, that means see here you can see the hydro has 5.8% generation, then wind PV has 0.8%. So all this generation or this generated power uh, will be consumed as a conversion loss. So this is a huge amount we are losing. Now the primarily our research is how to reduce these losses from device point of view. Now let me move to the next slide. So here this is a bit different context. So whenever we'll see any typical electronic application, so there are typically four sections in electronic application obviously, yeah. So at the very bottom of this any electronic application or any electronic appliance, there are of course a lot of materials, and then there are devices. After that there are a lot of circuits, and finally the system. So that means if we just go back, see just if you consider this, if I consider just the laptop currently I'm utilizing, see this is overall a system. Now inside this system there are typically several subsystem like power management unit, then this process microprocessor unit and all that. So then if you further dig into particular subsystem, you will find a lot of circuits. And if we further go into typical circuits, you will find a lot of devices. That means both active devices as well as passive devices. Now finally you have the materials, because all these devices are made of certain materials. Now in industry also the workflow is similar to this. What is this workflow? See, first the system specification will go to circuit engineers. Then circuit engineers will try to design some circuit as per the system specification. If they are unable to meet that specification, then they will go to device person. So then he will go and ask, okay, we need to have these device which can give us, these are the parameters. So then the device engineer will work, and if it is not possible to meet the requirements of circuit engineers, then the device engineers will go to material scientist. And material scientist or materials are the bottommost thing. So because beyond material, we do not have any other scope to work on. So if we just recap the starting point, where we have mentioned that this is all about wide bandgap semiconductor. Now see, to meet all the emerging application requirements means, let's say earlier the kind of application we had in case of power electronics, we had the requirement of 100 volt breakdown voltage. Now nowadays we have the requirement of 10,000 volt. So we need some device which can sustain 10,000 volt. So for that, of course, this silicon or like material is not suitable. So I'm just giving you an example, because silicon, in reality, silicon can be utilized for this 10 kilovolt application, but there are a lot of disadvantages. But the thing is, for all this emerging application, so the standard materials, that means your silicon is unable to meet. That is why we need to leave the silicon and we need to move towards different semiconductors. So although there are other challenges when we go with the other non-silicon semiconductors, we'll discuss them shortly. So this is again another workflow to realize any electronic application, which is of course very interdisciplinary in approach. Because see, that is why nowadays again in IIT Mandi and I think in our country, so this interdisciplinary or research is very important, because now this electrical or electronics or mechanical, they are not separate anyways from, of course when we are studying it is different, but when we will do research we need knowledge or the support from all other branches as well. So we should have some understanding. If still if we are let's say electronic engineers or electrical engineers. So here, see, the everything is starting with this. This is called AP ready silicon wafer in case of all non-silicon semiconducting industry. So then these are practically, this is the job of material scientists. So mostly the chemistry people or physics people, they are involved in this kind of research. But still, if you want to realize this overall application, if you just take my example, see, I need to do all this, like I need to develop this material, I need to process these devices, finally I need to characterize these devices and get the application. So that is why this interdisciplinary research or knowledge is very important for today's this industry. Now, if we look at the electronic revolution, so as we all know that with the invention of that bipolar junction transistor in the year, I guess, 1947 by that Shockley, Bardeen and Brattain, so this revolution, this microelectronic revolution has started. Again, they got the Nobel Prize, I think, around, I think in year 1950 or 51. So this first revolution in electronics was the is the micro revolution, and the fundamental component of this microelectronics is this CMOS inverter, and as well as this DRAM. Now, if we look at, there is another parallel revolution. It is started a little late than your microelectronics revolution, and it is started with the invention of thyristor, I think around 1960. So the fundamental component of this power electronic is a power switch and the typical energy storage devices like inductor or capacitor. Now, these are the typical component of any power electronic system. So we have a source, then we have a load, and in between we have a converter. And this converter consists of different topological components, then which it is controlled by some following some algorithm in communication with the central computing system. Now, what is this power electronics? I believe most of you know, but still the power electronics, the fundamental role of power electronics is to regulate the flow of electricity. Now, depending on the power rating and the functionality of this different power electronic component, we are identifying them. So, but when selecting any power electronic component, the primary parameter that we should look into, they are like, I think these three parameters are applicable not only power electronic component, it is applicable for most of the engineer, like when selecting most of the engineering apparatus or component. It is the efficiency, size and cost. So these three are the determining factor to select any power electronic devices or component. So this is again typical converter. So the first one is the linear power converter, and the second one is the switching converter. Now, converter means, see, let's say we are supplying 100 volt, and at load we need, let's say, 50 volt. So in case of linear power converter, you can see just we can utilize simple resistor and through that register, that resistance value we can select, so that 50 volt drop will be there. So the another 50 volt will get at the load. So just simply this is the voltage divider circuit. Similarly, this current this circuit also we can get this our desired voltage. Now this the same purpose we can for the same purpose we can utilize this switching power converter. So what is the problem with this this voltage converter? This is typically, this is buck converter. So the high voltage level to low voltage level we are getting when utilizing this linear power converter. The problem is when utilizing this resistor, so they that 50 volt drop is there, but they are these are all power dissipating element, these resistors. So that means if we look into the overall efficiency when converting this 100 volt to 50 volt, so then the efficiency is very, very poor, because you are intentionally dissipating that additional this power through this register. But when you are utilizing this power converter, that means when you are utilizing this switch, so this switch means, the simply you need to change your duty cycle. That means on off period of this switch, and by changing this on off period, and you can get the same conversion, that means 100 volt to 50 volt. But the important thing is, in this switching power converter, the efficiency is very high when you compare this switching power converter with the linear power converter. Because see, ideally this switch should have zero power, like this switch should not consume any power, because when it is in on state condition, there should not be any voltage drop. That means it should conduct all like a very high current. No voltage should drop across the switch. That means if we consider just simply V into I, that means you have infinite I, but no V. That means you have zero power loss. And similarly, when this your switch is in off state condition, then there will be no current flowing through your device or flowing through your switch. Again, you are getting P equals to V into I, again equals to 0. So now you can see, compared to this linear power converter, if we utilize this switch, how the efficiency will increase. Now this switch, in place of this switch, we are using those active devices. That means nothing but the transistors. So here we are utilizing transistor, and those transistors are utilized as a switch, and we are getting a very high efficient power converter. Now the problem, again, in the coming slide, we'll see that these switches or these devices are not ideal devices. So because in off state condition, it can flow certain amount of current, and also in on state condition, it could have certain voltage drop across the device, so which will lead to a power loss in on state and off state. So those we'll see shortly. So this is a once again just a evolution of different power semiconductor devices. As I mentioned, so it all started with the invention of thyristor in the year 1957, and again you can see, based on the different voltage level, we have different devices as well as different application. And another interesting thing from this chart is the material. See, initially, I think you know that even the first transistor, which was invented by those three scientists, it was made of germanium. It was not made of silicon. Then actually silicon come because of its low cost as well as some other advantages. So then you have this silicon, but as we are moving towards higher different application, then different materials came into picture. So initially, then around 1975, that gallium arsenide is another compound semiconductor, and it also has band gap greater than silicon. So although the gallium oxide cannot be say as a band gap semiconductor nowadays, because nowadays we have this gallium arsenide has band gap of 1.43 electron volt, whereas your silicon has 1.1. So, but still, this silicon carbide and gallium nitride has a band gap of around 3.3. So that is why nowadays this gallium arsenide cannot be called as a wide bandgap semiconductor. But still, then in the year 1975, first this gallium arsenide came. Then you have the silicon carbide, then gallium nitride, and nowadays, so this is 2010. Now in 2020 or 2021, we are having lot of other emerging power semiconductors. That means your gallium oxide, aluminum nitride, even diamond. So this is another classification based on the power and the frequency of your power electronic devices. So the interesting fact from this figure is, as we decrease the frequency, our power rating will increase. Similarly, as we increase the frequency of our device, the power rating of our device will decrease. So this is the normal observation. So then this is another classification. I'll not go into detail. So this three-dimensional figure, perhaps the most important figure till now. So obviously considering the power electronic devices. So here we have three axes and with the three basic parameters. One is current, another one is voltage, and another one is frequency. Remember, when we are utilizing any semiconductor devices like MOSFET or diode, so and these diodes or MOSFET we are utilizing as a switch. So obviously this current and the voltage will come, and then the switching frequency is coming because we are utilizing these devices as a switch, not as a linear regulator or something like that. So these three parameters are the fundamental parameters of any power electronic device. Now, in this three-dimensional this graph, if we look at this three-dimensional these bars, like at the very back you have this thyristor. Thyristor is one device, one solid state. Hello, am I audible?
Yes, now it's audible.
Okay, actually, again, this power issue. We have a power cut here in the campus. Anyway, okay, let us start once again. So this at the very back we have this thyristor, that solid state device. If you see, this device could have very high voltage and very high current rating. See this current wise, it can flow more than 1000 ampere of current, and the voltage wise it can sustain 10,000 voltage. And this thyristor is made of silicon. But what is the problem with this thyristor? The problem is with the frequency. Because if you look at the frequency, this thyristor cannot operate at very high frequency. It will operate below 100 hertz. Now, if we go towards this higher and higher frequency, Now if we see, like if we just consider the previous evolution of power semiconductor devices, so as we move towards the higher frequency, so different devices, different modern or emerging devices actually came. Now the problem with this all modern devices like IGBT, then MOSFET, now if you see, the voltage and current rating reduces significantly. Although it can operate at very high frequency, but the voltage and the current rating decreases. Now from the application point of view, ideally we need very high voltage, very high current, as well as very high frequency. Okay, from this power electronics from point of view or application, considering the application, we do understand that it needs high voltage and high current rating. But what is the importance of high frequency? The frequency, we need this high frequency because, see, the first advantage is your the associate this this, when you will operate your active device at high frequency, you also need different parasitic component, like different associated component like capacitor, inductor. So if you operate any capacitor, inductor at very high frequency, the size will reduce. That means if we can operate our these solid state devices at very high frequency, so the overall size of our power electronic system will reduce. And not only that, at very high frequency, the efficiency of this overall system will also increase. So these are the main reason why we need devices made of like, or the devices with the high frequency. But the problem here, you have already noticed that we can operate this MOSFET or IGBT at a relatively higher frequency, but the voltage and current rating will reduce. But our objective is to get high voltage, high current, as well as high frequency. How to get these three high? The thing so these are typically all like all these devices like thyristor, GTO, IGBT, MOSFET, these are all made of silicon. Now here comes another another motivation for your this wide bandgap semiconductor, because now your devices made of silicon cannot give you the high voltage and high current while operating at high frequency. Now now you need to leave your this silicon and you need to move to your wide bandgap semiconductors such as gallium nitride or silicon carbide, or these most emerging semiconductors like gallium oxide, aluminum nitride, or diamond. Because when we'll move to those wide bandgap semiconductors, it can give us very high voltage, high current at high frequency. So that is the motivation why we are moving towards wide bandgap semiconductors and leaving the silicon. So see, this is another. Okay, just hold for a second. I need to take some important call. Just time coming. Okay, sorry for the interruption. Well, so in this context, so there is this is an opportunity considering the power electronics and the power devices. There is no single device structure exist at this time which is suitable for all application. See, that is why, although we are moving towards wide bandgap semiconductors, even with the wide bandgap semiconductors also there are other disadvantages. to meet all these requirements, but to some extent it can meet. That is why we are moving towards wide bandgap semiconductors. So let us see them. So okay, so these are the some basic specification which you already mentioned, that voltage rating, current rating, as well as the switching frequency. And then these are the gain, bandwidth, and power rating is the specification when we are considering these devices, that means active devices, as a linear device. Because linear device and active device or this switching device, see, you know that transistor. So transistor has typically three regions in output characteristics. You have this cutoff, then your saturation, and then you have active region. Now, when you will operate your device in the active region, then you will get the linear regulator or linear device application. But when you will operate your transistor in cutoff and saturation, then you will get the transistor application as a switch. So these are the application, and obviously we need this high voltage, high current. But the problem we'll see in the coming slide, that leakage as well as the on-state resistance. And obviously we need fast switching and all other parameters. Now, as I mentioned in the previous slide, see this to build or to fabricate any device for this modern or emerging application, we need to consider all this material, these parameters. So these are the material requirement for fabricating any modern or emerging power electronic device. So what are the parameters? So see this energy band gap, this is a material parameter. So then this mobility means, you know, how easily your electrons will go through your devices. Then similarly, breakdown field is also related with the energy band gap, which should also be very high considering the power electronic application. And another important, this your parameter for your power electronic application, like material parameter, that is the thermal conductivity. Why this parameter is important? Because we have all experienced that heating issue. Like again, when operating our mobile, laptop, we know this these all electronic devices are getting heated up when operating for a long time. But so this thermal conductivity, so the higher will be the thermal conductivity of any typical material, so it will be easily able to emit the heat. But the lower will be the thermal conductivity, the accumulation of heat in this in that particular material or the devices will be more. So more will be the heat accumulation in your device. The overall performance of your device or your circuit or overall your system will degrade. So that is why, so we need some material which has higher thermal conductivity. Now, if we consider, these are the typical wide bandgap semiconductors. See, this is the blue one is the silicon, and then gallium oxide, orange, this gallium oxide, this orange one, then your this gallium nitride and silicon carbide. So these are all power semiconductors. Now, if we look into this pentagon structure, and in this corner of this thermal conductivity, see, the best thermal conductivity you can have from the silicon carbide. That means if we operate silicon carbide made devices at same specification, that means at same voltage and frequency, so this silicon carbide devices will be more like a most cool device. If we obviously when we are comparing just this four material. Now, when we'll have some materials made of this gallium oxide, that devices will suffer from this heating issue maximum, because it has very low thermal conductivity. It will not be able to emit the heat which will accumulate. Again, you know why the heat is being produced within the typical device, because again, this I square R issue typically. So again, if you go to the material point of view, there are something different thing, like the heat is nothing but the vibration of atoms, just as we are discussing the materials. So that is why you should know that the heating in material is nothing but the vibration of atoms. So the vibration of atoms means when the electron will move through the material, higher will be the vibration, it will be scattered. The electron will be scattered. And when the electron will scatter, what will happen? The resistance of the material will increase. Because just imagine, like if any electron is going through atoms, and those atoms are vibrating. So it will be difficult for those electrons to go through those atoms. So your overall your resistance and the performance will degrade. Now this is another important two-dimensional graph for your power semiconductor devices. Here you can see in the x-axis we have breakdown voltage, and we have on resistance in the y-axis. Now see, on resistance, the definition of on resistance is, like your switch has two state. One is on state, another one is off state. So when your switch or this device is in on state condition, it will provide you some resistance. Ideally, the resistance should be zero. Ideal for if you have ideal switch, so there should not be any resistance at all. It should flow infinite amount of current, but obviously in reality this is not the case. So the device will have certain resistance. So actually this resistance will give you that voltage drop when your switch is in on state condition. Remember, P equals to Vi. Now in on state you do not expect any V, that means V on. So, but still, due to this on resistance, that due to this sufficient or this certain amount of on resistance, we have certain V on. Now that V on multiplied by your that high amount of current which is flowing, that will give you the on state power loss. So that means if we want to reduce this on state power loss, that this resistance should be as minimum as possible. Now, if we look into this breakdown voltage, this is just straightforward concept. Obviously, we need higher breakdown voltage for this high power application. Now, ideally, where we should have, like where towards which corner we should go. Ideally, we should go towards this corner. Why? Because in this corner, whenever we'll go towards this corner, we'll get maximum breakdown voltage, but at very low on resistance. Okay, so that means we'll get very low conduction on state loss, but at the very high breakdown voltage. Now this, if we considering this fact, if just look at this parallel lines, this parallel lines is for the silicon. That means if we make any device made of silicon, the devices will be somewhere here, like the devices or the performance of devices or the breakdown voltage and on resistance of the silicon made devices will be somewhere here, like either on this straight this line or before this straight line. Now if we go towards wider and wider bandgap semiconductors, that means we know that at least now that silicon has 1.1, then gallium arsenide 1.43. This is the bandgap. Then SiC has 3.29, gallium nitride 3.34, beta gallium oxide 4.9, and diamond has around, I think, 5. So if we take wider and wider bandgap semiconductor, ideally we move towards this desired corner. That another way to look at this diagram is, when we'll take wider and wider bandgap semiconductor, we can reduce the on state this voltage. Okay, so just simply I think just if we consider this 1000 volt of breakdown voltage, now you can see any devices made of your gallium arsenide which has a 1000 volt breakdown voltage, it will provide you a very high on resistance. But the same 1000 volt breakdown voltage device, if we can make it utilizing gallium oxide, see, look at the on resistance, the reduction in on resistance. So that means the on state loss will reduce if we utilize this beta gallium oxide. So this way actually we are reducing the losses utilizing these wide bandgap semiconductors. But after saying all this motivation for for our this emerging wide bandgap semiconductors, we have the limitation. Of course, like everything is not free. We have a lot of other challenges like cost and reliability. Because you know that silicon is the most earth abundant material, so the cost wise beating silicon is very challenging. We cannot beat silicon in terms of cost. Now another factor is reliability. What is this reliability? So here I would like to point, see, there are two concepts. One is the performance, another one is the reliability. These two concepts are different. Performance means, let's say we have one device and we are just characterizing this device. That means we are checking what is the breakdown voltage, what is the on-state resistance, what is the frequency. So at this moment, our this particular device is giving us this specification, but that does not mean after 5 years or after 10 years we'll get the same performance from this same device. That means there might be some degradation with the time. That is called reliability. Reliability means whether the same performance will get after 5 years or 10 years or not. So considering this fact or this reliability, this all these wide bandgap semiconductors is they are suffering because of course the from the maturity point of view and all other thing, these are lacking considering the silicon. So I guess these are something I have already mentioned, but still, see, these are the some requirement from a ideal power device, considering the zero power dissipation. So you can see the when your device is off state. So this is ideal switch, ideal power switch. That means when you are having off state condition, see there is a no current flowing through the device, and all the voltage is appearing across the device. And when you are having on state condition, so then there is a very high current flowing through your device, but there is no voltage across your device. So you will get a zero power loss both in on state as well as off state. Another requirement is this T on and T off. What is T on, T off? This is time to make your switch off and time to make your switch on. So that T on and T off should also be zero ideally, but we'll see in reality this is not zero. So then that is called switching loss. Because again, once again, if we try to recall in one of the initial slide, we mentioned the devices has two losses. One is conduction loss, another one is switching loss. And in conduction loss, once again, you have two types of losses. One is on-state loss, another one is off-state loss. Now, overall, see these three losses, how they are coming. This is off-state loss, this is on-state loss condition, and this is the switching loss condition. And these are the other two parameters which are expected from a from ideal power switch. Now, so typically, if we look at our power switch, so this is the behavior. See, there is a current. There is a leakage current flowing when it is in off state condition. That means if you just multiply this current with this voltage, so you will get some power loss, that is off state power loss. Once again, when your device is on state condition, so although we have very high amount of current flowing, but still you have some amount of voltage drop, and this voltage drop is coming due to that on resistance. That on resistance multiplied your current IR, that is the VF. So this voltage and this current will once again give you very high on state loss. So okay, so this is on state loss, this is off state loss. And now if you look at this current and voltage waveform, so it is not going to zero or this high to low. So there is some delay when going from on state to on state, on state to off state. So due to this, in between time T1 to T3, these devices will provide you lot of switching losses. So basically, from research point of view, our main objective is to reduce all these losses, and how to reduce these losses as much as possible. So this is considering this ideal power rectifier. Ideal requirement is this. This is a rectifier means simple diode behavior. So this is the ideal requirement, but we know that the idea, typically we are getting this kind of behavior from our diode. So there is a V on, and there is also some I off. So that will lead to those on state as well as off state losses. Similarly, this is the ideal switch transistor, but see, this is the actual one. So here we have this on resistance, which will give us on state losses, and as well as here we will have some leakage current, so that will give us the off state loss. Okay, so it is already 4. So should I continue, or I can stop here? I think. Yes, are you there?
Yes, sir.
Yes, sir. You can continue.
Okay, so then actually these are the basics. Now I can, okay, I'll just show you some of our research. So this is the overall the research approach we are taking at IIT Mandi. See, as I mentioned earlier, so we are a group working on wide bandgap semiconductors, but application wise we are fabricating these power devices. The one which we have I have explained till now, and we also work on deep UV photo detector. So this is optoelectronic device. So using these wide bandgap semiconductors, you can also get these optoelectronic devices. So now these are the other approach. So we are developing this thin film as well as this nanostructure, and we do utilize a lot of equipment like pulse laser deposition, chemical vapor deposition, as well as electrospinning. So these are the different tools which we are utilizing to fabricate these power devices as well as the deep UV photodetector. Now these are something I think which we have already covered. This is the same. Okay, so here we have something interesting. So in gallium, this is gallium nitride HEMT. So in gallium nitride device or power devices, mostly we are utilizing this HEMT. What is the full form of HEMT? The full form is high electron mobility transistor. So this is not a MOSFET. This is a modified MOSFET. We know, I think, how does our typical MOSFET work and all that. So, but these gallium nitride devices, what we are utilizing as a power device, they are not MOSFET. So they are called high electron mobility transistor. So why it is called high electron mobility transistor and how does it operate? Let us explain. So the journey all started with the transistor. We know that this is a 3-terminal devices where we have this transfer of resistor, and that is why this transistor. And we know we are having this source, drain, then gate, and on the gate we are applying the voltage to have our challenge through which our drain current will flow. Now, see, all over this MOSFET, this fundamental, this basic device, the current flow mechanism is the drift current. We know there are two types of current flow mechanism. One is drift current, another one is the diffusion current. So diffusion current typically we see in case of bipolar devices such as PN junction diode, bipolar junction diode. But in case of MOSFET, here the current flow mechanism is drift current. So where the current of current density, so drift current density, that is the J, primarily depends on this N, that is the carrier concentration, as well as the mobility. That means how quickly those electrons will move through the challenge. So the how many carriers we have in the channel and how easily those carriers can move between source to drain, that will decide how much current we'll get. Now see, already we know that in case of power device we need high current. So now the question is how to increase this current density. Then only we can get overall high current. So either we can increase this carrier concentration in or this mobility, because this Q is the charge density which is fixed constant, and this E is the electric field or the voltage that we are applying across the source and drain. So these are the two fundamental parameters. So by designing a proper transistor, we can increase. Whenever we will be able to increase these two, we will get the higher current for a given voltage or electric field. Now here comes the high electron mobility transistor. So in case of high electron mobility transistor, we do have engineered this device in such a way so that we can increase this carrier concentration as well as the mobility. Let us see how. So in case of high electron mobility transistor, we have this two material. So below, so where also this is a three terminal device, source, drain, gate. But below the gate we have barrier, and below the barrier we have the buffer. What is this barrier and the buffer? Fundamentally, these are made of two different material having two different band gap. So whenever we have these two material having different band gaps, we will have some quantum well. So I'll not go into the detail, because obviously it is not that whenever we'll have different material one on top of other, so we'll have quantum well. There are certain conditions when we'll get the quantum well. Now why it is called quantum well or this triangular potential well? Because the electrons will be trapped in this well. So the electron, see this dotted, this white line represents the electrons. So that electrons will now flow between source and the drain. And in this, actually this quantum well or this potential well will have lot of electrons, which is not possible to have in case of just normal MOSFET. So one, that means we can have better carrier concentration. And another interesting thing here, just think, see electron in this case will only move towards this direction. Like that means this is also called two-dimensional confinement of electron. Why it is two-dimensional confined? Because electrons cannot move from in this direction. In this G direction or in this vertical direction, electrons cannot move because it is confined in a well. So electrons can either move in this direction or out of this plane. That means the plane or vertical to this computer screen. So electron has this two-dimensional motion. So this third-dimensional motion, this vertical motion is absent in this case. And what is the advantage? See, when electron will move in all three directions, it will be scattered by all three directions. Scattering means resistance. Like its mobility will degrade, so then you will have a degradation in the current density. Now, since these confined electrons can move only in two dimension, so it will face scattering only two-dimensionally. That third dimensional scattering is absent in this case. So that means the mobility of these carriers confined here is increased. Now see how we could get higher carrier concentration and higher mobility just by utilizing this potential well or quantum well concept, and which is coming due to this different band gap material, that is barrier and the buffer. So in this way, we have increased carrier density. Now, initially this HEMT concept came in case of gallium arsenide material. So in that case, we have this aluminum gallium arsenide, which has a higher band gap than the gallium arsenide material, which has a lower band gap compared to this. And in between these two material, we have these confined electrons, which will carry the current between source to drain. So again, nowadays this L gas it has very high mobility. So this figure, just to give you the idea, in case of silicon, the electron mobility is 1400 centimeter square per voltage second. Now you can see here it is almost 7 to 8 times higher than the silicon mobility. So typically this kind of transistor nowadays used in case in all our smartphones. Why this is again a different context? Because in we know that we are having currently 4G mobile and 4G this network. So then 5G is coming, then 6G. So basically our this frequency, operating frequency is increasing. This is something different than this particular presentation context. So higher will be the frequency, that electrons should have high mobility. So that is why these transistors are nowadays used in our smartphone, from where the signal will go to our nearest base station, and this is called RF front end of our mobile. So there actually we are utilizing this transistor. So these transistors are very good for making those power amplifier and low noise amplifier for this higher generation mobile. So nowadays we are utilizing the same concept in case of gallium nitride, because in case of gallium nitride, so this is see, this is the you will perhaps those who are in power electronics domain, they will see a lot of discussion on GaN device. So the GaN device basic schematic is this one. So where we have this aluminum gallium nitride, which has higher band gap than this gallium nitride, and in between this aluminum gallium nitride and gallium nitride, we have this quantum oil, and that quantum oil has lot of carriers and very high mobility, and due to that we are getting very high current. And as well as this since this material is made of gallium nitride, which has high band gap, the breakdown voltage is also very high. So now you can understand, see, in terms of voltage, in terms of current, these devices can sustain very high, this device can provide very high specification, as well as since this mobility of this carriers is very high in this quantum oil, so it can also operate at very high frequency. So this is the advantage of our wide bandgap semiconductors. So okay, so this is another topic because so most of these HEMT-like devices, high electron mobility transistors, they are normally on device. Normally on device means there will be channel or between your source to drain. But if we just quickly remember the concept of MOSFET, we need to apply some gate voltage, some positive gate voltage, then only we will have the current flowing between your source and drain. But now in case of HEMT, we already have some channel, so there will be always some current flowing between source and drain without applying any voltage at the gate. So what is the problem? See, this is the problem, means you always need to keep applying some negative voltage here, then only you can remove all the carriers in the channel, and then you can get the you can switch off the transistor. So this is a problematic in case of power device. So so now for this kind of HEMT device, there is although nowadays this challenge people have already modified, and they have engineered this. So this enhancement mode operation getting in case of this HEMT devices is I should say was a difficult task because of this normally on operation and carriers. So so I did some work on this how to make this devices enhancement mode, or so you can see here. So this is the transfer characteristics. What is the transfer characteristics? The characteristic between drain current and the gate bias. So normally in case of your D mode device, see, our threshold voltage is negative. So that means we need to apply some negative threshold voltage to make our drain current 0. But to have this enhancement mode operation, so we need to make this threshold voltage positive. So that means our this current or this characteristics should shift towards this positive voltage direction. So this way I have done like a lot, like some study during my PhD. So and proposed one this concept how to make this transistor enhancement mode. And so here basically we have I have incorporated different layers, like you can see uh, this is one so here we have another quantum well. Actually I think next figure will be the better one. So here we have utilized, so this is the quantum oil. So where see this is the quantum oil, one quantum oil, this is the another quantum oil. So here actually we have incorporated two quantum oil to have this enhancement mode operation. So this is the summary. So here we have here by utilizing this quantum oil, like second quantum oil, we could get this positive threshold voltage or E mode operation, which is required for our power electronic application. Now very recently we are working on this gallium oxide based devices, as I mentioned. So first see, this is some research approach. So this is the instrument, the basic instrument which we are utilizing. This is called CVD, or chemical vapor deposition. So here we are actually developing the material. So this is the schematic of that system, and these are the few process parameters. So as I mentioned early, so this is completely interdisciplinary research. So see, just before this I talked about this current, voltage and everything. So now the figure or the data you are seeing, these are all material related data. So this is called X-ray diffraction result. So what is the purpose of this data? So it shows how good material quality you have developed. So this is called X-ray diffraction result. So these peaks represents whether that is a good material or bad material. Because always remember, to fabricate a good device we need very high quality material. Or I think you know that this semiconducting, these solid state materials are crystals. So crystals means there are atoms, and those atoms are properly arranged. So if we have some misordered atoms, so then that device will not be a good device. There will be a lot of problem considering the reliability. So that is why, so before fabricating a good device, we should confirm whether that material we are developing is of high quality or not. So then this is the just the morphology, or the top surface image. So that surface should be very very smooth. So otherwise there will be a lot of performance degradation. So this is some device which we have developed on sapphire substrate. So sapphire is this okay. So just in this context I should mention, for all these non-silicon devices, see, silicon devices, the whole device is typically made of silicon. But for all these non-silicon devices, we need one platform from on top of which we'll develop different material. Like in gallium nitride, this device, the bottom or the platform is made of typically silicon. So on silicon, we are depositing this gallium nitride material, and then we are depositing this aluminum gallium nitride material, and we are getting that electrons confined at the interface, and we are getting that high mobility, high carrier concentration, and high current. So you see, as we have seen, that we cannot beat silicon in terms of cost. So that is why we are utilizing the platform or the substrate as a silicon, because silicon is the most inexpensive. So now on top of silicon, we are developing all these wide bandgap semiconductors. So then only the cost wise we can get the advantage. Otherwise, if you want to develop this entire device made of gallium nitride, the overall price of the device will be very high. And obviously, being an engineer, we have the trade-off, that whether cost or the performance. So now this, just to reduce this cost, people are utilizing this silicon. So silicon cannot be avoided. So these are the some research, and this is a different research where we are utilizing silicon with the different orientation. Like orientation means all this substrate, the atomic arrangement are different. So you can see here the silicon 11100 and silicon 111. So the atomic arrangement in this silicon is different than this atomic arrangement. Now on top of this silicon, we have developed this beta gallium oxide like wide bandgap semiconductors, and this is a vertical Schottky diode. So this is the gold. If you deposit gold metal on gallium oxide, so you will have Schottky contact. Schottky contact means, I think whenever there is a contact between metal and semiconductor, either you can get Schottky contact or ohmic contact. What is the Schottky contact? Schottky contact means the current voltage relationship here will be non-linear. And what is the ohmic contact? When the current voltage relationship will be linear, so that is called ohmic contact. That means, see, when we are depositing aluminum on silicon, and if we measure the current voltage like relationship in this contact, it will be a linear relationship. That means in the positive direction, if we keep on increasing the voltage, current will keep on increase. In the negative direction, if we keep on increasing the voltage, current will keep on increasing. But in this contact, in the first quadrant, that means whenever we'll keep on increasing the voltage, current will increase. But in the reverse direction, or that means in the third quadrant, when we'll keep on increasing the voltage in the negative direction, the current will not be increasing. It will be blocked. So that means there is a Schottky contact or non-linear behavior. So this is the Schottky diode. So this is another actually diode. So the PN junction diode, but this is a Schottky diode. The same non-linear behavior we are getting just by utilizing metal and the semiconductor. So these are some study based on different substrate. So okay, I think these are this is another research. Okay, I'll stop here, I think. So overall, this gallium oxide, materials, this gallium oxide like wide bandgap semiconductors, these are very promising for next generation power electronics application, considering the breakdown voltage and the frequency. And for all this emerging semiconductor, we are utilizing this sapphire and silicon as a substrate. That means the platform we are utilizing this sapphire and silicon. Sapphire is another material like silicon. So on top of this sapphire silicon, we are developing this gallium oxide, this wide bandgap semiconductors, and we are trying to realize this all emerging power electronics application in terms of current, voltage, and high frequency. So that's so these are the funding support I received to do all these researches, and that's it from my side. Thank you. And if you have any question, please let me know. I'll be very happy to address your question.
Yes, sir. Thank you so much. That was really a wonderful session. I hope all the participants got insights in this domain. So now I will take questions we received from our attendees. Sir, may I start taking those questions?
Yeah, please. Yeah.
Sir, there is a first question from Orko Prabhu Datto. Sir, what does epi-ready mean?
Epi-ready. Yeah. So this epi terms is actually coming from epitaxial. Now, what is this epitaxy? In all the non-silicon or this compound semiconductor, this term is very common. So the epitaxial is, I think, a Latin word. The epi means above and taxi means ordered manner. So you have noticed that we are developing the material. So below we have one material like gallium nitride. On top of that, we are depositing aluminum gallium nitride. So these two materials, they are different. Materials are different means the atomic distance. See, fundamentally all the material parameters are related with the distance between two atoms. This is of the order of some angstrom. Like in case of silicon, the distance between two atoms is 5.43 angstrom. Now, this AP ready means the substrate we are taking that is ready for the developing material. Like the substrate is silicon, and on top of this, if we are depositing, let's say, gallium nitride. So this substrate silicon is ready for the gallium nitride like materials. And AP means that atomic arrangement between your substrate and the depositing material should be same. Otherwise, what will be problem? Let's say in the bottom material, the atomic arrangement is different than the top material. So it is like building a house. So the this, you have the pillars below your this ground level. Those pillars should be exactly same with the pillars you are having in the top floor. So otherwise you will have you will destroy your home, or your house. So similarly, this in case of atoms also, like the bottom, that the substrate atomic arrangement should be equal to the top layer atomic arrangement. Otherwise there will be lot of defect, and those defect will hamper a lot. Like the whole device performance will degrade. Whatever theoretically you will predict, that let's say you are expecting that this current, this voltage you are expecting, but you will nowhere close to that current voltage because of those defect. So that is why all this platform or all this substrate should be AP ready. Otherwise the top layer will be defectful, and you will not get the desired performance from your device. So this is the answer. I hope I could answer. Yeah. Next question.
Yes, sir. Next question. Sir, next question is asked by Shreyoshi Shen. Sir, what for the converters, in which case switching loss is minimal?
Yeah, is this visible to me? Is this is this?
Yes, sir, these are the questions.
Okay. So for the converter, in which case switching loss is minimal. Okay, so I think it depends on the converter topology, and from the device point of view, there will be some loss. So I don't work on the switching topology. I do not have much idea on the circuit point of view, but from the device point of view, I can say that fundamentally that R on, or the on resistance, should be as minimum as possible, so that you can get minimum on state loss. Then the leakage current, because see, whenever your device is under this reverse bias condition, there will be still some current flowing through your device. It is not exactly zero current that will flow, but ideally it should be zero, because your device should be in off state condition. So that leakage current should be as minimum as possible, and it depends on a lot of other factors. In case of Schottky diode, that carrier this minority carrier concentration, then the temperature is another parameter which will decide all these losses. So higher will be the temperature, higher will be the carriers, and higher will be the losses. So again, to reduce the switching loss, for this switching loss, from the device point of view or material point of view, what I can comment, see, the carrier lifetime is the primary parameter. Carrier lifetime means, so whenever you generate one carrier, that means from very fundamental point of view, generating one carrier means you are taking one electron from the valence band to conduction band. And of course, after some time, this carrier it will recombine, so it will get annihilated, so it will recombine with the whole. That means this carrier or the electron will jump again from the conduction band to valence band, so there will be no existence. Of course there will be other carrier generation, but the time between your generation to recombination, this time will decide your switching loss. So this factor, now you can understand, or you can see overall how the performance parameter all are correlated with the all fundamental parameters like conduction band, valence band, carrier lifetime. These are all I would say like mostly the science people they are working on. Like, but still see how they are really important to get a good device. That is why this knowledge, this thing, these are all very important. I hope this I could answer your point, and you can also let me know if you have more question. Yeah, yeah. Next question: what are the limits of a power switch? Limits of a power switch means in terms of what? Limit say in terms of which parameter you are saying, that I need to understand. Like, say switch has all those parameters. In case of power switch, this current, voltage, and then your switching frequency. Now of course if you just ask me the maximum limit, the maximum current, maximum voltage, maximum frequency, and they are mostly decided by the voltage, the breakdown voltage, at which you will operate, that will be decided by the breakdown your band gap of the material. Now your current typically, if you consider this unipolar device like your MOSFET, so the current has those two components that I have shown, that carrier concentration as well as the mobility. So now those two material parameter will decide what will be your maximum current flowing through your device. And now in terms of this, if you ask me what will be the highest frequency, so the frequency will be decided by the carrier lifetime primarily. So like now you can understand like what are the material parameters you have, and using those material parameter, what are the device limit you could have, like what are the limits in terms of voltage, current, as well as the frequency. So this way you should correlate. Now if you change the material, your all these limits will change. Okay, so next I am moving to next question. In the current trend, which material is used mostly in power electronics? In the current trend, which material is used mostly in power electronics switching device? What are the advantages it has over the previous material? So the current, okay, this is again a good question. So there are few wide bandgap semiconductors, that means non-silicon wide bandgap semiconductors. See the in one presentation where I have shown that that graph between on resistance and the breakdown voltage, there we had several materials like silicon carbide, gallium nitride, gallium oxide, diamond. So to precisely answer to your question, silicon carbide and gallium nitride, in terms of device and materials, they are most mature. I think the most mature one is the silicon carbide. So because see which device you will use, that depends on the maturity of your material. Again, if you just recall that particular slide where I have shown that system, circuit, device, and then material. So considering this silicon carbide and gallium nitride, this material and device wise, it is mostly research. Most of the research has already been done, and mostly the people are working on the circuit and system domain. So if you want to work on circuit and the system domain, the best material is the silicon carbide and gallium nitride. And now if you want to work on power device and materials, so then gallium oxide, aluminum nitride, diamonds, they are the materials that you should work on. So I think I could answer your question. The material mostly used on power electronics switching device. What are the advantages? And so this is the answer. Like again, in this upcoming electric vehicle technology, this gallium nitride and silicon carbide is going to play a significant role, because of the again these all. Now see this correlation, this is nice correlation, or it could be a very good take home message for all of you. See, in the electric vehicle, the everything should be like, if you are having something on board, that means on the vehicle, it should be very portable, right? So that means the size should be very small. Now, the graph where I mentioned we need to operate at high frequency, there we mentioned that higher will be the frequency, lower will be the overall system size. Now you can see the significance of this all wide bandgap semiconductors. If we could operate at very high frequency, overall the system size will be small, then it will be very portable, which could be very ideal for our this electric vehicle application. So these are all correlated. Okay. Now next question is how to know the know a material has
Hello,
indirect.
sir. Hello.
Yes, yes, yes.
Yes, sir. I am Bikram Kumar Samanto. Sir,
Yes.
what are the effect of the temperature in this kind of materials? Sir, you only mentioned about the voltage, current, and the frequency. And what are the effect of the temperature in this means power electronic switching devices?
See, temperature, obviously, all those in all this performance, mostly we have considered the room temperature. Now, from the fundamental point of view, if we increase the temperature, there will be more electrons jumping from your valence band to conduction band. That means what? You will have more carriers in the device. And another thing is, I have also mentioned that temperature is nothing but the vibration of atoms. Like, see, you should see all this factor at very microscopic level. Then only you will be able to explain all the phenomena. So at this very microscopic level, temperature is nothing but the vibration of atoms. So higher will be the temperature, higher will be the vibration. That means higher will be the scattering. So carrier scattering. That means your this mobility of your electron will reduce significantly, but your overall carrier concentration will increase because of the more just simply you can consider, all this semiconducting material has covalent bonds. So higher will be the temperature, those bonds will break and we will have a lot of free carriers. So then you will have a lot of carriers. So now you see the leakage current. If we talk about leakage current, what will be the impact of the temperature if we consider the off-state characteristics or off-state loss? So then the leakage current will be more because of the available or the more carrier concentration. So that means overall the loss, off-state loss, will increase. Similarly, in case of on-state condition, your this carrier scattering, or this scattering with the phonons, or this is the lattice vibration is called actually phonon. So phonon, photon, electron, these are the some other concept. So in the on-state condition, if we increase the temperature, higher will be the vibration, higher will be the scattering, lower will be the mobility. That means overall your current will degrade. So the current, let's say at 5 volt, you are expecting 100 or let's say 1 ampere of current from your gallium nitride device. But at high temperature, you may not get the 1 ampere current. You may get because of this scattering, which is coming all the way from the vibration of atoms. So this is the correlation. Could you understand?
Yes, sir. Yes, sir. Yes, sir.
Okay. So should I move to next question? Then how to know whether a material has indirect or direct band gap? So this is some characterization tools we need to utilize. Typically for direct band gap, this semiconductor, we have for this gallium oxide research, we are utilizing UV visible spectroscopy. So this is nothing but we are just incidenting some light. Light means nothing but the photon. So then there is a transition. Whenever the photon energy or the energy which is coming from the light is greater than the band gap, so band gap energy, then there is a transition. So looking at this transition or this from the spectroscopy result, we can easily determine what is the band gap and whether this is indirect, direct. And another thing, I think indirect and direct, this band gap, I think you can utilize this PL, photoluminescence. In the PL, also what we are doing, we are exciting the material with different photon energy or different light, and then we are observing when the electrons are coming down from the conduction band to valence band, because whenever the electrons are coming down from the conduction band to valence band, it will emit some photon. So in case of this direct band gap semiconductor, will get exactly same amount of photon energy like its band gap. Otherwise, in case of indirect band gap semiconductor, will not get the exactly same amount of energy. So this way, actually, we can judge whether this particular material is direct bandgap semiconductor or indirect bandgap semiconductor. Okay, so next question is, can you explain how widening the band gap is affecting the reliability of the semiconductor device? Okay, see, if I just restate this fact, the reliability means, as I mentioned before, the same performance, like how long the same performance will persist with the same device, like the performance we are getting today, whether the same performance will get after 2 years, 5 years, or let's say 10 years. It depends on the maturity of your technology. What is the maturity of technology? Maturity means, see, like all over the world, lot of people are doing lot of researches now. Not only the academic institutions like us, there are a lot of industry who are investing highly on this semiconducting research. So more will be the research, the maturity of this certain technology will increase. Let's say just for as an example, we can take this gallium oxide. Gallium oxide, just recently, I think just 5 years back, people have started to utilize this gallium oxide material as a semiconducting material. So now still there are a lot of like research going on to make this material more mature. So mature means process technology, what temperature, what synthesis technique, what process flow we need to maintain to get the best quality material, so that we can get best quality device out of it. So straightforward, if I want to answer your question, the reliability is directly associated with the maturity of the technology. Now just simply you can consider this silicon transistor invented around 1950s. So for the last 70 years, people have done a lot of things, a lot of research, a lot of R&D in the industry they have done. So that is why the maturity wise, silicon is the most mature technology. Now this gallium oxide compared to that is only 5 years old material. So obviously people are doing a lot of research, and with the research, this material will be more mature, or the device will be more mature, and obviously in future it will be a very reliable device. So it depends on the maturity of the technology. Yeah, I hope I could answer your question. I guess there are no more question. Any more question if you have, you can directly tell me.
No, sir, there are no questions as such.
Okay.
So,
Okay.
sir,
So I'm stopping this screen sharing. Okay.
So now we are at the end of our first event. After this wonderful session, we would like to thank Dr. Ankush Bag for taking some of his precious time off and conducting this tech talk on wide bandgap semiconductors for emerging bandgap power electronics. Thank you so much, sir. On behalf of the IEI IEM Students Chapter, Electrical Engineering Division, we would like to present you with a token of thanks. It's been a pleasure to have you here with us today, sir. So, Shagnik, will you please present a token of thanks?
Is my screen visible?
Yes, your screen is visible.
Thank you, sir, for being with us here today. And this was a really very nice session. From IEI Students Chapter, this is the token of thanks that we have for you today for this event. Thank you, sir.
Okay, well, thank you, and I am accepting your this token of thanks, and it's my pleasure to present before you. And the question you have asked is really very encouraging for me also. Thank you, thank you, all of you.
Now, we would like to move on to the next part of today's event, the CWC installation ceremony of IEI IEM Students Chapter, Electrical Division for the term of 2021 to 2022. I would like to introduce you to our next host, Shagnik Ghosh of second year Electrical Department. Over to you, Shagnik.
Okay, I'm leaving then. Yeah. Is that fine?
Okay, sir. Thank you, sir.
Yeah, thank you.
So thank you, Tonishti, for handing me over. Just a second. Okay, so good afternoon, everyone, all the teachers present here. I am Chagnik Ghosh of Electrical second year, and now I'd like to take over the installation ceremony for the CWC of the year 2021-22. Due to the global pandemic crisis of COVID-19, we could not organize the installation ceremony as tradition dictates. However, with the whole country adapting to the situation and turning towards various online platforms for acquiring knowledge as well as for official purposes, we decided to embrace this medium as we have done with our events on this term and organize the CWC installation ceremony. Before we move ahead with the ceremony, let us know who we are by a video that was created by the students of the chapter.
The Institution of Engineers, IEI in short, is the largest multidisciplinary professional body of engineers. Established in 1920 with its headquarters located in Kolkata and incorporated under Royal Charter on 9th September. IEI IEM is a student chapter under IEI. We organize different types of events throughout the year. Let's have a look of some of our events.
Here we have a few glimpses of the events conducted by IEI IEM Students Chapter, including several webinars, poster presentation competitions, circuit tricks, app tech, and our flagship event, Engineers 2020. You will catch several familiar faces here of your batchmates, seniors, as well as previous CWC members as they talked about their experiences in IEI.
Is my screen visible again?
Yes.
Yes, it's visible.
Next, I would like to thank Professor Dr. Tapush Kumar Datta sir, Head of the Department of Electrical Department, IEM, for being present with us today. Professor Tapush Kumar Datta sir has always been a strong support and a source of constant encouragement for our chapter. Sir, I would request, would you please like to say a few words?
My dear students who are present in this gathering, and Professor Devashish Jana, I am immensely thankful to all of you for organizing this program. It should be put on record that IEI Electrical Engineering Student Chapter is doing a marvelous job since a few years. Last year was quite vibrant. Despite the pandemic situations, we could not meet physically, but even online also, this chapter was doing a lot of activities to churn the young mind about the different aspects of our technology. Actually, it should be emphasized that only curriculum activity will not make a successful or complete engineer or engineering scholar. You must inculcate yourself your this knowledge to solve different types of problems, and it gives an opportunity to everybody for having this experience of organizing an event, how to organize an event, how to run organizations. That means the students chapter executive committee of last year. I would extend my sincere gratitude and thanks for keeping the activities of IEI student chapter active, and I would congratulate and extend my best wishes to the coming, that means our 21-22 executive committee, to keep this tradition up and increase the activities more. The more and more students, the executive committee should have a missionary vision, to involve more and more your friends, students of electrical engineering, so that they get the flavor of it, they get the advantage, or they gain the advantage of this type of student chapter. Different types of competitions you are arranging, ingenious, your flagship event you are arranging. There you motivate all your friends in your classes to join one and all, so that everybody gets the benefit of such a student chapter. So, on this installation ceremony of your executive committee, I extend my thanks to the outgoing committee and wishes good luck for the coming committee. Thank you.
Thank you, sir, for those kind words of yours. Now, it is my pleasure to inform you that IEI student chapter has had a successful term from the year of 2020-21. Let us take a minute and look back at the various accomplishments that we have achieved in spite of having pandemic and lockdown. IEI IEM student chapter never stepped back. They continued to host innumerous successful events. Among all the negativities during pandemic, we tried our best to spread some positives through a series of quarantine events. We organized 6 tech and non-tech events under the banner of QuarantCon. We had TechScribe, technical article writing competition in the month of May 2021, followed by our next event, Illusion 2020. It was a logical reasoning competition. Articulus, which was an art competition to encourage the hidden artists within us. Quarantine events included Criticize 2020. It was a competition on movie and book reviews. Keeping in mind the activities people were up to in the lockdown, we had Quarantino, a video making competition to encourage the hobbies of our participants. We ended our quarantine events with a technical quiz, having Mr. Bikram Kumar Samanto as our quizmaster. He is an alumnus of our college, currently engaged with his PhD from IIT Delhi. At the end of quarantine events, we had a couple of webinars. The first webinar was conducted by Team Applex.in on app development. Our next webinar was conducted by Professor Dr. D.P. Kothari sir on trending topic of energy environment problems faced by the third world countries and their probable solutions for sustainable development and alleviations. Since last year, a new initiative has been taken by this chapter to organize AppTech. AppTech 2020 was a competition of general aptitude. We organized this event to prepare our members for various competitive exams. Our next event was an innovation challenge called Innover Technical Project Presentation Competition, the finest platform for all prevailing technocrats, where we ourselves learned about a lot of marvelous technologies. This challenge even rendered us to learn that despite having unfavorable conditions, how not to stop learning all the way. Innover was followed by a couple of alumni talks on higher studies and a journey to ONGC by Bikram Kumar Samanto and Vivek Singh Bora respectively. These are some pictures we took from IEI newsletter where our events have been featured. A proud moment for all of us. Now, I'd like to pass on the mic to my co-host Shreyoshi Chakraborty from second year electrical department. Over to you, Shreyoshi.
Thank you. Hello everyone. I'm Shreyoshi Chakraborty from second year EE department. We would like to thank our past CWC members for their effort to organize such a wonderful event and for all the guidance. Now, we would like to move to the presentation of scrolls for CWC batch of 2020 to 2021. Shayantan Chandra, as a president, he held the committee with his extraordinary decision-making skill with a strong vision. He also took the charge of effective execution of strategic goals for the development of the chapter. Moving to our next committee member, Moitri Banerjee. As the vice president, she led the committee with her zeal and innovative mind. Her calm demeanor with strategic goals execution is highly appreciated. Moving on to our next committee member, Orkopubu Dotto. As a treasurer, he excellently managed the financial affairs with sincerity and allowed the chapter to successfully organize a great number of events last year. Moving to the next member, Shalini Mondor. As the R&D head for organizing webinars by esteemed professionals to presenting and arranging project competitions. With her passionate curiosity, she lived up to their roles. Next, Trijoni Dash. As a secretary, she executed efficient functioning of the committee. With her excellent management skill and facilitating interactions with the committee members is highly appreciated. Arvil Sen, our another R&D head of this chapter, he managed all the events successfully with a calm hand. We greatly respect his patience as well as diligent mind. Moving on to our next member, Shaptoshi Bhattacharjee. As a membership coordinator, his commitment to continuous guidance, creating a value source for the students is highly appreciated. He is an exuberant individual who played an instrumental part in this chapter. Next. Tanishta Chakraborty. As co-peer head, she lived up the event with her creative thinking and quick decision-making skills, sailed us through these tough times. Next, Teoshi Shane. As the peer head, she came up with really innovative skills in this unprecedented time. Her insolent hard work, determination, and smooth sailing through critical situations with calm demeanor was truly commendable. We congratulate and express our gratitude to the former CWC for their contribution to the student chapter and wish them a successful career ahead. We will forever be grateful to you for your guidance and leadership. Now, I would like to pass on the mic to my co-host, Teoshi Shen from third year EE department. Over to you, Teoshi.
Sashi, you are not audible.
Seriously, if you are using a earphone, just disconnect the earphone and try.
Hello, am I audible now?
Yes, yes, you are audible.
Okay. My apologies for the inconvenience. So now I would like to request Professor Debashish Jana sir, Faculty Advisor, IEI IEM Students Chapter, to take the ceremony forward. Sir?
Hello, can you hear me?
Yes, sir.
Okay, fine. Uh, uh, First of all, I would like to thank all of you, especially my sincere thanks and gratitude to my HOD sir from the Department of Electrical Engineering. Obviously, and I've found some of my fellow colleagues who have attended few minutes before. Uh, and obviously, the students who are the members, IIM members are just going to be members for the short time. So first of all, after the beautiful, the very significant talk which is delivered by Dr. Onkush Bag, we are about to actually the time which actually saying that we should conclude the entire event by 5. I think as per the schedule which we have made, you actually made that. Okay, so we are actually running out of time, so I will not spend much more time. I will just take 1 or 2 minutes to highlight some areas that this committee, which are going to be formed, what the activities, or what are the motivations they should input to other students. Okay, so here, first of all, I just want to thanks the ongoing members who are actually um, uh, giving the duties to the new members who are coming into the governing committee of the IEI student chapter for this college. Okay, so actually, if you look back, we have established this chapter in 2016. Okay, it is almost 5 years we have uh, go through that different situations. But last years, that means from 2020, that we have faced that is tough time to organize the events, which actually very much important for the students, as well as the students who is actually uh, coming to modify or accommodate themselves in engineering educations. Okay, so on that occasions, the plan, something has been shifted towards organizing this event as not the physical context. We are going to introduce that kind of events through the virtual platform. Okay, so and we have do a lot of things. We have experimented a lot of things that you all are witness of that from last year actually. Okay, so during this short span of journey, we actually evolved and designed the chapter activity in very diversified way that anyone can get best thing out of it. Okay, and even that is most important thing, that nowadays you will find, if you start from the journey, that there may be one or two chapters in our entire college. Now you will find lots of chapters. Okay, in number of chapters. But thing is that I think all the chapters have the same importance. Okay, but it particular uniqueness. Okay, you have to project your thoughts or motivations so that you can have the compatibility where you want to put yourself. Okay, so I think who are taking obviously you will find attending this kind of activities or taking membership will get a certificate which will give on you the marks or the points. That is the simple thing that I do not highlight on that particular points. Okay, or you can get a certificate attending these activities. Just this is not the boundary we want to create by these activities. Okay, so thing is that I suggest the new members who have right now to be appointed for the new academic year for the core committee. Okay, uh, thing is that you have to take some lots of initiative. Already we have take the initiative to launch different programs. So and you follow, if you follow that, we we also expand our the activity from the technical to some communication skill improvement too. Okay, so here actually any kind of society expects from any engineering graduates or BTech students to demonstrate the skills in communications or having some interpersonal skills that obviously enhance to get jobs obviously, and it's some point of view self management is to be required as well. So thinking on that, you have to have different type of experiments that you can create some activities and put others on that activity or put others to take part on that activity. So on that particular context, I think Sayantan and his team has started a new event, that is Quarancan. On that event, that time it was very much successful. That it was a modular type event, but this gives very impact to those students who are staying home and taking part in the different activities. So this is the thing that HOD sir also mentioned, that there should be some motivations. Okay, there should be some motivations, and imparting these motivations to others, that is the task which we will be going to impose for the core committee members. Okay, so that's all from my end. I thanks all the organizing committee for successfully executing different types of activities, or even like we are a series of talks like that. So keep moving on, and I and our department or college will expect more such kind of activities for enriching the students, not only the members, but also who are actually taking part, not being a member of IEI IEM student chapters. So, and one more thing I have just forget that we have some alumni members also, that is chapters alumni members as well as college alumni, and I also thank them that they have actually conceived those ideas, and this is actually carried over by the current members, which right now we are actually observing. Okay, so thank you all. Thank you. All the best.
Thank you, sir. Now, I would like to call our seniors to narrate their experiences of being a part of such an illustrious family. Starting with, we have our previous CWC members for the term of 2019-20. Shalini Mondol, the ex-R&D head, she organized many webinars and project presentation competitions with her diligence. Shalini Di, over to you.
Thank you. Good afternoon, everyone. As I've already know that I am Shalini Mondol and I served IEI as the membership coordinator in the year of 2019 and 20. And the last year I was the R&D head. So my journey started as an engineers volunteer in the year of 2018, and then being selected as a CWC, I organized many events. I really miss those late night discussion about the events, and the bonds we made with our seniors and juniors, that will be really missed. And IA has so many benefits, but in my case, IA really helped me a lot improving my soft skill. So I would really thank to IEI. And coming to the end of this tenure, it is very sad that I have to say goodbye, as it is a major part of my college life. And thank you. And the most important thing, best of luck to my juniors and the new CWCs, and wishing you a very successful and eventful tenure. And thank you.
Thank you, Shalini. That was for your guidance. Now we have Orko Prabhu Dotto, the ex-treasurer. Orkoda.
Hello, am I audible?
Yes, you are.
Yeah. So, hi, my name is Arkur Datta, as you know. So, I have been part of the IEI student chapter since 2017, from my first year of college. Within the first month of college, engineers was held, and I somehow got a chance to be part of this photography team, where I met my senior Shamayanda, Srijanidhi, and Bikramda. I met a lot of my seniors in my first year of college. I didn't know anything then. I just had a camera and I went there and I started recording and I started taking pictures, and that's how I got introduced to IEI. When I got into the second year, I became a volunteer, as every month most of us joined IEI as a volunteer. She guided me a lot. I worked with her on the mural that we mostly did for the engineers, and also participated in few of the events. In my third year, I got selected as an integral member of the CWC to work on the event during engineers, and I leaded the team who made the mural, as you saw in the video, for engineers that year. It was one of our successful murals, and we were very proud of that. Then, and in coming to our fourth year now, I became the treasurer, as I was nominated to become the treasurer. It was a great experience as a whole for 4 years, because I think IEI will be always a very big part of my life, because it taught me everything I know in college. Most because I was a very closeted child, as from my school days I didn't participate in events or anything, but from IEI I started participating. I participated so much that I missed classes also. I went out of classes. So I'll ask my juniors not to miss classes, but do take part in events as such and participate as much as possible, because this will help you grow a lot more than you can think. It will build up your soft skills. It will build up your critical thinking. It will give you the confidence to speak. Like this kind of talk I'm giving now, the speech 4 years back I couldn't have. I would have been shut quiet. Like I would have been so quiet that I guess Srijanidhi knows very well about that because she was very close to me. So with that, I wish the new CWC best of luck. I hope to see great things from you. I hope the chapter grows immensely, and thank you for.
Thank you, Orkoda. As you very correctly said, that mural painting was a great experience, and our introduction to IEI happened through there. Next, we have Moitri Banerjee. She was the ex-vice president, and she led the committee with her zeal and innovative mind. Moitri Di, are you there?
Hello, everyone. Am I audible?
Yes.
So my name is Moitri Banerjee, and I have been the vice president of IEI for the academic year 2020-2021. So first of all, I would like to say one thing, that I am not very good at giving speech. So please forgive me if I make any mistake. So my experience with IEI for the first time was as a participant. When I was in first year, I participated in the engineers for the first time. And as engineers is full of different interesting events like technovision, circuit tricks, curiosity. So that was the first time I took interest in IEI, and I participated in a couple of events. And after that, when second year, my department got shifted to electrical, and after that I started participating in different workshops, technical talks, different technical events organized by IEI. And in third year, I joined IEI as CWC member. So from then on, what I have experienced throughout my journey in IEI has always really helped me to develop myself to a person what I am today. Because when I was in school, I never was a part of any organizing team, or I didn't have such experiences. So when I joined IEI, all those things were very new to me, and I was not at all expert at doing such technical things or organizing events. And I used to be very introvert and shy kind of person. My interactive skills were very bad. So I would say one thing, that all the seniors present at that time, Choyanda, Srijonidhi, Shamanda, everyone has always helped me, guided me, and of course our faculty advisor, Professor Devashish Jana sir, so that they have always given me the space so that I could learn the things. I have learned so many things, like how to organize events, how to handle situations, how to make plans for a big event, and I have made lots of memories. I would like to mention one thing, that engineers, which is the flagship event or the biggest event organized by our society, we could not organize engineers this year because of this pandemic situation. And last year when we organized engineers in February 2020, I remember just after the event, within 15 days the college got shut down all of a sudden because of this corona and lockdown things. So eventually Engineers 2020 has been the last college event, offline college event of my entire college life. So, and I would say that it has been one of the best memories of my college life, because during the time of engineers, all the seniors, juniors got reunited, and we walked as a team. We walked with so many enthusiastic people. We had fun with each other. We made memories, and we learned so many things. So all these things are going to be with me for the rest of my life. And I would say that our journey has come to an end today, but all the memories I have with IEI and all the things which I have learned are always going to be with me, and IEI will always have a very special place in my heart forever. And I am very much thankful to all the seniors, our faculty advisor, Professor Devashish Jana sir, my friends Shayanton, Shalini, Orko Prabhu, all the juniors, Srijoni, Arvil, Shoptorshi, Shreyoshi, Tanishta, for being so nice to me, for being very supportive to me. They are all very nice to work with. And just I would like to wish best of luck to the new team. And with that, I would like to conclude here, and thank you for listening.
Thank you, Maitridi. That was indeed very kind. We all benefited a lot under your guidance. Next, as already mentioned, comes one of our esteemed IEM alumnus, Mr. Bikram Kumar Samanto, who has done his master's in renewable energy from IISc Shibpur and is currently pursuing his PhD from IIT Delhi. Bikram da, over to you. Bikram da, hello.
Yes. Good afternoon, everyone.
Good evening.
Good evening. Good evening, sir. Good evening, my juniors. So, at first, I want to congratulate my 2021 pass out batches juniors. During the pandemic situation, they did well to organize various types of events. And then I want to congratulate the new members who are going to be a part of the 2021-22 members who are going to be the CWC members for the upcoming years. The Engineers 2020 memories are still fresh. After that, no physical events are happening. And also the IEM IEI memories. With that, I want to say that I am a student of 2018 batch, but my interaction with the IEI IEM chapter started from the 2016 since it started. After that, I am not a core committee member, but being a CR, I have learned a lot from the IEI IEM chapter. How to organize the events, how to work as a team, and how to develop the bonding with the seniors, with the juniors, with the interaction with all, and how to guide, how to motivate the juniors for the various kind of events. And in our event where we have some technical events like paper presentation, poster presentation, some innovative type idea, from that our technical skills are developing. From the events like the aptech, where the aptitudes from various competitive exams, from that we have learned a lot. We have learned a lot from the technical and non-technical various things we have learned from during the IEM IEI chapter. That's it.
Thank you, Bikram da. We still learn a lot from you even now after all this time. Next, we have an ex-president of the chapter. She is vivacious, she is intelligent, and she is one of our guiding lights. Introducing Sriyoni Datta on the stage. Over to you, Sriyonidhi.
What was that introduction? Okay. First of all, congratulations to all the new CWC members, all the who are going to be the CWC members, and the passing out batch. That was a brilliant batch, a brilliant team. Moitrey, Sreyoshi, Orkosh, Shayantanto. I don't have any words for you. Shalini, Arvil. I cannot see Arvil's video, but then you're a brilliant batch. And I started off my journey as a volunteer. Party class bunk kore. And Orko was there. Orko and me actually started off together. He was the videographer and I was a volunteer. And it has been a marvelous journey. Shamayan joined me a year later. And I guess me and Shamayan was the best ever team I have ever worked in. Me and Shamayan it was amazing working with him. And the whole team, of course. You will have fights, you will have disagreements, you will stop talking to your teammate. It will be a roller coaster ride, but at the end of the day, it will be a memory that you will cherish for your whole life. And just make things right before you pass out. It's just a year. I'll not say you don't fight, you don't disagree, you do, but then make it right before you leave. That's it. All the best.
Thank you, Sriyonidhi. Next, we have the ex-Vice President of IEI IEM Students Chapter for the term of 2019-20 and also an IEM alumnus, Mr. Shamayan Bhattacharya. He is currently working as a software developer in TCS Limited. Shamayanda?
Okay, hi everyone. Good evening. So, thank you to the present CWC or the ex-CWC team for giving me this opportunity to be back with this whole thing. Okay, I would say that office life is really boring. Okay, it's just work and work. It's really to be like being back to this whole thing. Okay, where everyone is freely sharing their all opinions and everyone is talking about their certain experiences. It's really good to be back. Okay, and I would like to congratulate the people who are going to be the new CWC members. Okay, you have a really a great opportunity to develop yourselves in all kinds. Okay, like technical things, the interpersonal skills, your communication skills. So you're getting a great opportunity. So be execute this opportunity properly and learn from all the sources you're getting. Okay, and talking about my experience and as a CWC member in IEI, it has been one of the best parts of my life. Okay, not only my college life, but of my whole life. I have enjoyed everything throughout this time. Okay, working under my seniors. Okay, making my juniors work and not make them work like make them go through different responsibilities. Okay, but it was really an awesome thing. Okay, and I wish that this whole pandemic thing gets over as soon as possible, so that you all can get back to college and lead the best times that we had. Okay, so I would end there. I'm really excited to meet the new CWC. Thank you.
Also, call us when you're having fun offline.
Yeah,
Sure.
Even if you
Obviously.
don't call, we will be there.
Obviously, we will call you. Lastly, we have our ex-president from the batch of 2021, Mr. Shayantan Chanda on the stage. Shayantanda.
Thank you, Shreyoshi. Good evening, everyone. My name is Shantan Chanda, and as Shreyoshi said, I'm the president of the term of 2020 and 2021, and before that, I was the event head of the term of 2019 and 2020. What can I say? Everything that I wanted to say has been said by Moitre, Shalini, or Kokovo. So I don't have much to say, but I would like to just mention that it has been absolute pleasure interacting with juniors, seniors, uh, professors, as well as the industry professionals that have visited us for webinars. It has been an absolute pleasure and a learning experience interacting with them. In one sentence, I would say that II has been organizing events with fellow CWC members and having fun along the way, as well as gaining skills like managerial skills, interpersonal skills, communication skills, as well as the technical skills from the various workshops, webinars, and the project opportunities that I got from IEI. Meeting with alumnus like Vikram Kumar Samantoda, or our very own Bikuda and Joyanda, working on projects with them, working with Onkur sir on a project was also a very healthy experience of my life that I will cherish forever. I hope I can work with him again. And of course, organizing events, actually not organizing events, but the days before the events took place, when the all CWC we would debate on what to do, and then we will all get bored and okay, so let's order cold drinks, and then we will have cold drinks, and then we will and so through this process we will, how did we organize successful events? I don't have any idea, but we did. So that was a really beautiful experience. So thank you for giving me this experience and having the constant support of our faculty head, Professor Devashish Jana, and of course our HOD, Professor Dr. Taposh Kumar Dotto, who supported us throughout our term to organize events and giving us the freedom to do so. That opportunity actually helped IEI organize this many events. So so Taposh sir has been a big support for us. So thank you. Thank you, Shreyoshi, for giving me this opportunity to speak.
Thank you, Shantanda, and for personal thank you for introducing all of us in second year to IEI. Next, I would like you to continue with introducing the 2021-22 CWC members to us.
So let me thank you for giving me the honor to introduce the future CWC of IEI that we will be handing over our responsibilities to. We have Shaknik Paja, who will be the class spokesperson. We have Shoptorshi Das, who will be the membership coordinator. We have Rebecca Adhikari, who will be our public relations coordinator. We have Shreyoshi Chakraborty, who will be our public relations head. And we will have Shagni Ghosh for our secretary. Moving on to our fourth tiers, we will have Debojit Ghosh as our membership head. We will have Shantan Pal as our research and development head. We will also have Tonishta Chakraborty on for research and development head. We will have Shreyoshi Sen as event head. Allow me to introduce you to you Shoptoshi Bhattacharya, who will be a treasurer. We have designated the post of the vice president to Arvil Sen. And lastly, congratulations Srijoni Das for being the president of the term of 2021 and 2022. Best of luck to you for CW and please take the advice that the Professor Debashish Jana sir and Professor Dr. Taposh Kumar Dotto has given you and abide by those rules and take the responsibility of driving this chapter forward. Thank you.
Thank you, Shantanda. Next, I would like to call back Shreyoshi to enumerate our future plans. Shreyoshi?
Yes. Okay. With every closed doors, there comes a series of open doors with a number of opportunities for you. In this COVID situation, people faced a lot of problems to get along with the new normal, but it also opened various opportunities in a new way to tackle things. IEI IEM student branch, student chapter, electrical department, slowly but efficiently accustomed itself with the new normal. We organized a number of online events under the banner of Core & Co. We had also several talks to enlighten the knowledge of the students in between this lockdown. Due to the tremendous amount of response we received from the students, IEI IEM student chapter electrical department has come up with a whole new segment of events for the term 2021 to 2022. From the month of August, we will have our membership drive, also a workshop relevant to technology. In the month of September, we are going to have circuit designing competition along with webinar. In the month of October, we are going to hold our APTEC, our general aptitude competition. And in the month of November, we are going to hold Innovate 2021, that is a project demonstration competition. In the month of next January, we are going to have group discussion on relevant technological advancement. In February, we are going to have our flagship event, Engineers 2022. And in March, we are going to have election of our next CWC members and our annual general meeting, followed by technical talks and series of online competitions in the month of May and July. Now, I would like to invite our past secretary and new president, Srijonidhi, to conclude the session. Srijonidhi. Hello? Am I audible?
Yes, Srijani, you are audible.
You're audible, Srijani.
Okay. A very good afternoon, everyone. First of all, I extend my gratitude for considering me for this new role. It is indeed a great honor for me, and I hope I will do justice with my role. So, as we are at the end of this ceremony, It is my pleasure to extend sincere thanks to all the professors and seniors present here for enriching the ceremony with their presence. Also, I would like to thank the wonderful participants who have turned up in such a great number, not only from our department but also from the other departments with their active participation. I hope you enjoyed the talk and got an insight in the emerging area of power electronics. Now, last but not the least, I would like to thank our senior CWC for all the guidance and mentorship during the past year. And I must acknowledge it was really a great experience working under you. Finally, once again, on behalf of IEI IEM Student Chapter Electrical Engineering Department, I thank each and everyone for your time and cooperation. Thank you. Also, to capture this wonderful moment, I would like to request everyone to turn on their camera if possible.
সবাই সায়ন্তন, সপ্তর্ষি, Devojit, Shadnik, Kaja. I don't know him personally, but please turn up my cameras.
Actually, sorry, my camera is actually not working due to network issues. Sorry, Srijani.
Shaptashi, or 5 marks cut internal.
Yes.
Okay, Srijani, please take the snapshot. Is it done?
Yes, done.
Okay, with that,